This is a status report on Litton's high-energy Xaser directed energy weapon concept. We are calling it the HEX high-energy Xaser or high-energy Xaser photon cannon because it's a concept of a directed energy weapon which could be placed in geosynchronous orbit, would have a 25,000-mile range, and would be able to destroy any exo-atmospheric object such as a booster which has left the atmosphere, or a bus for deployment of RVs, or an RV in less than 1 second. I'd like to first give you the specifications for the ultimate plan of this weapon to show that it really does have a relevant potential, and then talk about the scientific background of it and how it could be proven in principle at very modest expense with a relatively small scale terrestrial experiment. The ultimately planned directed energy weapon would have a beam intensity on the target of 100 kilowatts per square centimeter, so that if it had a dwell time of 1 second, it would deposit 100 kilojoules per square centimeter. There has been public testimony before Congress that 75 kilojoules per square centimeter is lethal to any conceivable ICBM or reentry vehicle, and that's why I've adopted this figure as the intensity on target. Now, the range is supposed to be 25,000 miles from geostationary orbit, where we would put one or more battle stations. There is a theory of diffraction-limited optics which indicates that if we want a range of 25,000 miles and we want a beam diameter on target of 1.31 meters, then the focused beam as it leaves the directed energy weapon should have a diameter of 66 centimeters. And there is a theory that proves that that diameter is optimal. A larger or smaller diameter would result in waste of energy. The power in the beam would be 1.4 gigawatts, and the wavelength of the beam would be 44 angstroms, or 4.4 nanometers. The target dose would be 1.37 gigajoules, which would destroy the target by shock disintegration. Now, the beam will emerge from a plasma column which is 82 meters long, and the length of 82 meters is derived by a theory which suggests that the local gain will be 0.002 per centimeter. And if you exponentiate that, you get a gain of, you get the total length of 82 meters. The power conversion, I don't say what the power source is, but I want a power source of about 4 gigawatts. I will assume that that 4 gigawatts is converted to 2 gigawatts by some means that's about 50% efficient. And then I will assume that's converted to microwave beam energy by something that's 50% efficiency. Then I will assume that the microwave beam energy is converted to heating a plasma column at 65% efficiency, which has a very good foundation, which I can present calculations to support. And so that means that the overall efficiency of putting energy into the plasma column is about 40%. Now, if it's less, then we can raise the power that we start with. But the bottom line is that the beam will emerge with 1.4 gigawatts of power, and it will only diverge in 25,000 miles. It will only diverge to a diameter which is twice the diameter of the muzzle of the weapon. and we can prove theoretically that that's optimal. Now I want to review the history of this subject in the last 2 years to show that Litton's concept has undergone a few evolutionary changes, but basically we have not discovered any real flaws in it. The idea occurred to me in July of 1983, and we sent it to the Fletcher Committee in response to a solicitation from industry and academia for innovative concepts that might be helpful to the SDI concept. John L. Gardner, who was the Director of Defensive Systems in the Office of Undersecretary of Defense, sent me a personal letter 22nd of July, 83, saying the idea was sent to the DTST, Directed Energy Panel, and the idea was considered to have potential merit. Now that was just a 2-page version of the idea, a very brief preliminary version. Dr. Jerry Jonas, who was chairman of that particular panel, did talk to me on the phone and encouraged me to continue working on the idea and to document it further. Dr. Jonas has not seen this, but I now have a 30-page patent application in which I've documented many of the points that were not documented in the first 2-page version, and given literature references to what I consider to be all the key technical points. And as a result of this, I've improved the concept considerably. Now, I would like to show the general plan and then show how it's been revised. The original thing, we had a 300 megawatt power source. Now we have to have a 4 gigawatt power source, and everything else scales accordingly. The original concept, the plasma column was going to be 20 meters long. Now it has to be 82 meters long. The original concept, we were going to use carbon ions as the source ions, and that's carbon with 5 electrons stripped off, and then magnesium with 11 electrons stripped off as the lasing ions. And this carbon-magnesium scheme was demonstrated to work as a one-pass amplifier at a temperature of 400 electron volts, which is about 5 million degrees Kelvin, and at a density of 10 to the 17th to 10 to the 18th particles per cubic centimeter, which corresponds to pressure between 300 and 3,000 atmospheres. And this was done by Dr. Bhagavatula and published in the IEEE Journal of Quantum Electronics. Now, since then, I've found a much more promising scheme which has been published by Dr. Aprouzis of the Naval Research Laboratory, and which involves, instead of carbon and magnesium, it involves silicon and aluminum. And this Aprouzis scheme would lase at 44 angstroms, which is 3 times better in terms of 3 times higher frequency, a 3 times shorter wavelength than the previously mentioned scheme. Another change is that I've had to add an ingress to the plasma column whereby we can inject a stimulating 1 watt or 10 watt X-ray stimulus to get the thing started. That may not actually be necessary because I believe that spontaneous emission will start the thing, and so we only just need to make the plasma column a little bit longer, and we may not need this first portion. But then we really do very much need the other thing that I've added, which I did not show to Dr. Jonas because I hadn't worked it out yet. But we have what we call a plasma dynamic window. And the purpose of the plasma dynamic window is to allow the X-rays to exit from the weapon while the plasma column is confined by high-pressure gas. We're going to have to let a little bit of the high-pressure gas escape into the vacuum of outer space, and a little bit of the plasma escape into outer space, but this can easily be replenished by injection of cryogenic pills of the appropriate material exactly as the plasma is replenished in the MIT tokamak so very successfully that the Lawson criterion was met for the first time. So the idea of replenishing the lost plasma by pellet injection is an established technology. Now I come finally to the most novel and most innovative portion of the concept, and that is how to confine the plasma. Now I'd like to review what everybody thinks before I introduce this concept. There is a group in the Department of Energy called Advanced Energy Projects run by Dr. Gajewski, who funds half a dozen or more scientific research efforts on X-ray lasers, some of which have borne considerable fruit. For example, there is work being done at Princeton University, which has resulted in an amplification factor of 100 at a wavelength of 182 angstroms using C6 ions in November 1984. Also, there's work, for example, at Physics International on an imploding plasma, and that has been photographed in color. Now, most of the conventional schemes involve a transiently confined plasma, which may be compressed, for example, by an imploding magnetic field, and would then just be inertially confined for a few nanoseconds. The work at Physics International, I think, was about a 20 nanosecond pulse. And during that brief time, the plasma could be at kilobar or megabar pressures. There could be conditions similar to the inside of an atomic bomb explosion for a very brief time. And then the plasma would laze with a very high gain. For instance, a gain of 10 or 20 per centimeter instead of the gain I'm postulating, 0.0002 per centimeter. Now, the difference in my idea and the other ideas is to back off of the high pressure, to back off of the high gain, and to use a steady state plasma confinement technique that would permit long-term stable confinement so that the issue is what is the pressure that could be confined. And it's perfectly practical to use 300 atmospheres pressure, and in fact, people have designed plasma confinement schemes to work at pressures as high as 3,000 atmospheres, pulsed once every 10 seconds, and that falls apart from metal fatigue at the end of about 30 days. So if my scheme is supposed to be steady state at 300 atmospheres, that's just about 3 times the pressure in an ordinary steam boiler, and that's no particular stress on technology. Now, I'm very indebted to a scientist at the Naval Research Laboratory, Dr. Ray Elton, for publishing a general theory of X-ray lasers independent of the atomic number of the source and the lasing ions, in which he demonstrated as an approximation that the gain is linear in the density. And therefore, if I back off from the very high pressures in the transient schemes, I will get exactly from this one scheme published by Dr. Aprouzis of the Naval Research Laboratory, I would get a gain of 0.002 per centimeter, and therefore an 82 meters long plasma column would suffice. Now, the plasma column itself can be stabilized by magnetic feedback control technology, which was perfected in the Soviet Union, has been ignored in the USA, but was demonstrated by the Soviets on the 8-meter theta pinch plasma column in Great Britain. The 8-meter theta pinch plasma column in Great Britain was perturbed artificially so that it had an instability. And people came from the Soviet Union with their own equipment, and they hooked it up, and they damped out the instability using magnetic pressure feedback. So that technology, which has been ignored in the USA, is an established technology. The main technology that I want to talk about is the high-pressure gas confinement. The high-pressure gas confinement has been demonstrated in the Soviet Union by their greatest physicist, Pyotr Kapitza, who died at the age of, I believe it was 91 or 92 last year. Kapitza won the Nobel Prize in 1978. He was considered to be the greatest physicist in Great Britain on the eve of World War II, and Stalin called him home, and then he would not allow him to leave. And I have been told that Stalin kept Kapitza under house arrest for 10 or 15 years because he refused to work on the atomic bomb during World War II. Now, when Stalin died and Khrushchev became premier, Kapitza was rehabilitated, and according to Dr. Robert Bussard, who's documented this with references to the collected works of published works in several volumes of Kapitza, he became the chief scientific advisor to Khrushchev. And in 1956, Kapitza published a very important paper predicting the whole concept of strategic defense. His paper was called How Atomic War is to be Prevented, and it was published in the British journal New Times in 1956 in rebuttal to an argument by Bertrand Russell, the British philosopher who won the Nobel Peace Prize, the Nobel Prize for Literature. Kapitza disagreed with Russell's theory that the way to prevent atomic war was disarmament agreements. Kapitza said when he was Khrushchev's advisor that the way to prevent atomic war is to develop instruments of strategic defense which are capable of shooting down ICBMs and which, according to Kapitza, would require, quote, great energetics, unquote. In this paper, which was published in the Journal of Social, Political, and Economic Studies in the volume 9, number 2, in 1984, Dr. Bussard has documented the fact that ever since 1956, Soviet scientists have been working quite openly on strategic defense concepts. They published a book on plasma lasers with the title Plasma Lasers. They published that book in 1978, and when Aviation Week published a rumor that the United States had successfully tested an X-ray laser weapon pumped by a small nuclear bomb explosion, the Soviet scientists published an article analyzing the whole concept and saying it could be done with rods of certain composition. I've forgotten. I think they said the rods had to be zinc or beryllium or some particular metal, and they should be so many meters long and they should be so many millimeters thick. And they said that their theory indicated that such an experiment would be successful, and they referred to this 1978 book on plasma lasers. Therefore, the whole concept of using a plasma column as a one-pass amplifier of X-rays is not a classified idea, and I learned about it from the newspapers. And I decided to work on it when the DTST sent out a call for new ideas. The only thing that I thought I could contribute, I'm not an expert on the atomic physics of source ions and lasing ions for X-ray laser amplification. I simply take the word of established people such as Dr. Bhagavatula and such as Dr. Aprusis. What I do think I have to contribute is some very novel ideas due to Kapitza on how to confine the lasing plasma column. As a matter of fact, in 1960, Kapitza began a series of experiments which he finally published in 1970, in which he demonstrated a plasma column 10 centimeters long, 1 centimeter in diameter, floating freely in what he called high pressure gas, which was actually 1 atmospheric pressure, although he did some experiments at up to 30 atmospheres pressure, and maintained at a temperature, an electron temperature, of 1 million degrees Kelvin by the external injection of only 12.5 kilowatts of 10 centimeter wavelength, I beg your pardon, 20 centimeter wavelength microwave beams. He used a cavity resonator in which there was a particular spot that was well adapted for location of the plasma column, and he kept the plasma column from floating upwards by the Archimedes buoyancy principle, since it's like a hot gas bubble. He kept it from floating upwards by revolving the gas in the cylinder around its central axis, sort of in the manner of a blanket. And by revolving the gas around, he kept this plasma filament or plasma column in position. In 1981, he gave a new paper at the European Fusion Conference, which was held in Moscow, and Dr. Jerry Jonas told me that he was the preceding speaker, and he was there and heard Kapitza, who was in his late 80s, announce that he had tripled the size of the experiment. He had raised the length of the plasma column from 10 centimeters to 30 centimeters, and the diameter from 1 centimeter to 3 centimeters, and he had succeeded in raising the temperature, according to his published measurements, to 50 million degrees Kelvin. Now that's actually 10 times higher plasma temperature, electron plasma temperature, than we need for either of the two schemes that I have proposed for an X-ray laser. Either the Bhagavatula scheme or the Aprusis scheme would work at low gain at 300 atmospheres pressure at a temperature of 5 million degrees Kelvin, which is well below what Kapitza demonstrated in steady state for hours on end. Now, when Kapitza was alive, he was not very popular with the mainstream plasma physics community in the Soviet Union, who were more interested in magnetic confinement approach to plasma confinement. And a friend of mine did a year's postdoctoral study in Novosibirsk, and he told me that Kapitza was regarded as sort of an old fogey who was out of things by the younger generation of Soviet plasma physicists. And I have a written testimonial from Dr. Norman Rostocker, who's a professor of physics at UC Irvine, who has, in the past 20 years, visited Novosibirsk for scientific conferences no less than 8 times. And Dr. Rostocker says, the important question is about the plasma filament. Unfortunately, the work of Kapitza has never been confirmed by any other group. It was largely ignored by other Soviet scientists. And a friend of mine in Canada recently wrote a letter in November 1984 to Kapitza's successor as director of the Institute for Physical Problems of the Academy of Sciences of the USSR. And the 27th of November 1984, Professor A.S. Borovic-Romanov wrote a letter to Dr. Wright in Canada saying, at present we are re-examining the research on plasma conducted at this institute in developing Professor P.L. Kapitza's ideas after his departure and summing up the results thus far obtained. In view of these circumstances, until this re-examination has been carried out, it is rather difficult to enter into discussions concerned with the future development of this work. More recently than that, Professor Rostocker visited the Soviet Union and was told that the work of Kapitza has been completely dropped. Now, I think that's partly because the conventional plasma physics community doesn't understand how a hot plasma can spontaneously self-insulate itself from an ambient cold gas by means of an electrostatic triple layer which is maintained by external microwave energy. However, I have published a computer simulation which was published in the journal called Fusion Technology. I published a joint paper with Dr. Inkio of Stone and Webster Engineering Corporation where we demonstrated the possibility of spontaneous arisal of extremely large electrostatic fields in a thin boundary layer between a hot plasma and an ambient cold gas. At the time we published this, this was a more complicated explanation of the phenomenon than Kapitza's own explanation, which postulated what I would rather call a double layer in distinction to my own theory of a triple layer. However, my own theory of a triple layer has been totally vindicated in recent months, both by computer simulations and by direct experimental verification. And I would like to make reference to both items. There's a new journal edited in Australia by Dr. Heinrich Hora, who has edited many, many volumes on inertial confinement of plasmas. And this journal is called the Journal of Beams and Particles or something like that. And in it there are two papers, one by Hora and a collaborator, wherein he used a Cray-1 to simulate a plasma with inhomogeneities of density and temperature by means of a two-fluid model. And he showed that in very, very short times, like